My name's Stephen Chin. I run the developer marketing team at Oracle. And today I'm going to give you guys a gamut of different technologies, which you've probably seen as hype. I also run the Oracle Code Conference series, and so I see a lot of call for papers. I watch a lot of presentations around the world. And there's a lot of interesting technologies. You probably hear about a lot of interesting things at work around the water cooler or on the Slack channels. And the goal of this presentation is to arm you guys when one of your coworkers comes up with this crazy idea and he wants you to rewrite the whole application stack on something, serverless, blockchain, whatever. You can say, well, actually, I know a little bit about this. And then, actually respond and tell, some of the benefits and disadvantages of the latest technologies. So the 5 technologies we're going to cover, and this is going to be a lightning spin through because we only have 25 minutes, are containers, blockchain, chatbots, serverless, and machine learning and AI. So you're basically getting your whole conference in 25 minutes. Hopefully that's what you're here for. All right, so starting with containers. Of course, we need a picture of shipping containers because the Docker guys have made that the official analogy. But basically, this is how servers used to look like. You'd run things on bare metal. You just deploy things directly on the host operating system, install your packages, get hosts up and running. Nice and easy. But the problem with this is as you get larger machines with more multiprocessing capabilities, you want to be able to build denser applications and deploy things and also scale stuff. You need a better model for running different things on the same hardware, which is where virtual machines came in. So once you have virtual machines, now you have these little magical containers. You can run a bunch of things in parallel. They look like little independent operating systems. But the problem with this is you're introducing a bunch of overhead, and then you also have a lot of extra management because each one actually behaves like its own machine. So Linux containers solve this problem, and later on, Docker and other packages generalized it into a container model where rather than having a full virtualized operating system, you're just isolating different applications basically inside the main operating system. And so this allows you to deploy a bunch of applications. To them, they're in their own little isolated area, but actually they're running on the same host operating system. And you get a lot more density, and then you're saving all of this space in terms of processing overhead. It's easier to manage the servers. It's easier to test and deploy. You can run your containers on your local environment. You can deploy them to cloud environments. So this is a big improvement. And then it lets you do things like put a bunch of different applications and packages on the same machine. So if we get back to our list of different options for this, one of the ones I mentioned is Docker. They're kind of first to market. There's a bunch of ones that are part of the Cloud Native Compute Foundation, RKT, also Containerd, Kata Containers, Cryo. So there's a lot of different options for frameworks that you can use to deploy containers. And once you get your containers running on a very seaworthy ship, you can see I'm clearly a developer because I have bad art skills. The only problem with this is what if your ship sinks? So if you have all these applications running in a single container, then you end up like our folks at the end of the Titanic movie, without the love scene, just the crash. So the solution for this is using a framework which allows us to deploy containers or our applications to multiple containers simultaneously using something like Kubernetes. Then you can have your army of machines, all of which are getting automatically deployed to with your different containers. If one of them goes down, you're fine because you have your application running in different places with fault tolerance. You have something actually managing, sending requests to different machines. And then you can play games like, anyone here play Battleship when they were a kid growing up? Okay, so this is what you can do with your containers. You can play with your friends, take things down in production, and hopefully it all stays up and keeps working. All right, second technology hype, blockchain. This is not blockchain, but this is what most people think of as blockchain because it's the first real world use case, which is Bitcoin. Anybody own Bitcoins? Okay, well, you guys should have sold. Did anyone sell Bitcoins at the peak? Okay, you shouldn't have raised your hands, because now you owe us all beers. Because at the peak, Bitcoins were incredibly overhyped and overvalued. I sold my Bitcoins really early on, and I made almost nothing, because I thought that it was going to crash. And then it didn't crash. It kept going up. And then now if you still held on to them, then you're also in the camp of not really having a lot. And one of the challenges with cryptocurrencies is that the way it works is through mining proof of work. And the higher the value of the cryptocurrency, the more people are willing to put compute resources into mine. And then eventually you get this exponential curve where the amount of power consumed by the network of cryptocurrency exceeds, well, the 6 million US households. This was around the peak of Bitcoin. So the peak power consumption was a large portion of the US. Or another way of looking at this is it was the same power consumption as the entire country of the Czech Republic. So this is one of the areas where they're trying to improve the efficiency of cryptocurrencies. Ethereum is more efficient. But what we really care about with cryptocurrencies is not the actual technology for that. We care about the underlying technology for blockchain, which uses Merkle trees. So what this does is this takes all the transactions which you put into the network. It hashes them down to a single value, then combines this hash together with the previous block, with a nonce, with a timestamp. And then this gives you the next block, the next candidate block in the network. And then the miners, by majority consensus, select what the next block is. And this technique for a distributed ledger is incredibly useful for business-to-business applications. So cryptocurrencies are an example of public blockchain. What we care more about as developers is private blockchain, where we can take the same technologies and apply them to supply chain, apply them to finance. The main difference with private blockchain implementations is that you're going to get faster transaction times. You'll get the ability to put unlimited amount of data in transactions. You can do smart contracts. And you get, of course, privacy, because you can control who's part of the network and then also what data is visible. There's a few different examples of blockchain frameworks, which you might see. Hyperledger Fabric. So this one is an Apache project. It does consensus pluggably, but you can do transaction-level consensus, smart contracts in Go or Java, cryptocurrency with chain code. And this is also the blockchain implementation used in our Oracle Cloud Blockchain Service. A couple other cloud vendors use this as well because it's highly configurable. R3 Corda is another blockchain framework which is really more focused on the financial industry transaction level for consensus. You can code your smart contracts in Java or Kotlin, but it doesn't support cryptocurrency. And Ethereum, besides being a cryptocurrency, also can be used for private blockchain. And this is becoming increasingly popular. It allows you to do smart contracts in their own language solidity. And of course, it has cryptocurrency built in. So these are some good use cases for blockchain. So, financial services, you can, like we mentioned, R3 Corda is good for this. Legal, medical healthcare, IoT. Another example which you guys might be surprised by is this one.
So this is one of the first batches of beer that we actually produce off of the tanks that are equipped with the sensors.
If we could track in one program or one data set the farmer, the field, when it was harvested, those field conditions, whether it was there was lodging of the barley, or whether what the temperature was that it was harvested at, even things like what nitrogen he put in the soil.
People are interested to know a little bit more of the story of what went into this beer.
So anyone familiar with Alpha Acid? Have you visited them on the peninsula? So this is a small microbrewery. They get great ratings on Rate Beer. So Kyle's the owner. The other guys you saw in the video, so one of them was Admiral Maltings. They're in Oakland, Alameda. And then we got a hops farm in San Jose, and we also worked with a yeast supplier, Giga Yeast. And these are all examples of local companies who, if you drank the beer, you'd never know that all these local products went into the beer. Using blockchain, all of these folks entered their information into the Oracle Intelligent Track and Trace, which is built on blockchain technology. As a consumer, you could scan a barcode, and it would pull back all the information on this. And from like a compliance, government, supply chain standpoint, all of it is, it's a transacted ledger, so you can actually make sure that the information put in there is exactly what the original suppliers entered. And for everything else, blockchain is probably overkill. You might just want to consider a relational database. All right, so next technology, chatbots. So this actually, I think this has gone beyond hype. This is actually something you see a lot of companies implementing, and it's been around for a while. Sales chat. That's probably the least interesting case. Messengers are a more interesting case, so a lot of people are using it for text messaging, transactions on phones, doing simple transactions. Often conversations are like this for buying flowers, booking flights, being able to do grocery shopping, but a poorly designed chatbot will end up with a conversation that looks more like this. Some examples of voice integrations with chatbots are Google Assistant, Amazon Alexa, and HomePod. So now you don't just need to type to chatbots, you can actually talk to chatbots with these technologies. And one of the things we've been doing on top of this is robots as well. So I do a bunch of the demos for our Oracle Code 1 conference series. And we have a demo where we use the Pepper robots made by SoftBank to communicate with our backend chatbot service. So then you talk to the robot, it sends requests to the backend cloud service, and then based on the scripts we've designed, so we put together a bunch of common questions, like maybe questions about the demos, questions about the conference schedule, things like that. Then you can ask the robot questions, and they'll intelligently reply, or like fall back on some generic responses, which are interesting. And if all else fails, you make the robots
check this out. Dance with me. Okay. Well, let's go.
So that's the best feature of robots, is when the chatbot fails, they can entertain the audience. OK, next technology we're going to cover is serverless. Serverless technology is not throwing away your servers like this. If anything, it's buying more infrastructure, buying more service, so we can host things in a cloud infrastructure where you're paying by the time used for services. In a traditional model, you'd be buying infrastructure, perhaps deploying with some sort of monolithic architecture, scaling by provisioning new servers, and then based upon your geographic spread of infrastructure, your end users are going to get response times based on the server they're communicating with. The goal of serverless is you just pay by the server time used. You use a micro-function architecture, so you're coding in really small increments. You get automatic scaling via some large pool of cloud machines, and then low latency because that pool of machines is geographically dispersed, so the requests can be provisioned from the closest server to the end user. And the ideal is this is what you'd like to see. So the red line is a traditional model where you have to buy infrastructure which goes underutilized because you're not fully at capacity, and then when you use that up, you buy new infrastructure. The blue line is what you'd like, just paying for what you need. So you're using the minimum amount of hardware to solve the use case and only paying for the server resources that you're actually utilizing. Like any good graph that you see at a conference, this is a tip for any other presentation you see. Graphs are all lies. There are multiple things wrong with this graph, and one of them is the fact that the curve on the line was entirely incorrect. The cost model for serverless is actually not like that. Typically, you pay more per request, and you also have to go through some sort of API gateway or some entry into the serverless framework. So you end up on a per request basis actually paying more than you'd pay for traditional infrastructure. That said, the other benefits still apply, and as a programming model, serverless actually makes it really interesting and easy to spin up new applications quickly. So it actually does have a lot of advantages besides just cost. There's a bunch of different frameworks for serverless technology. So AWS Lambda is the first to market. They tend to be the most proprietary, so you can only run things on Amazon Cloud. Google Cloud Functions can be emulated locally, so it's a little bit more open and allows you to develop locally and deploy, but it's not an entirely open source stack. Microsoft also has a serverless stack called Azure Functions. They've open sourced their entire stack, so they're the most open on the set here, although they're still running some proprietary extensions in production. We also have a serverless framework at Oracle called Cloud Functions. The Cloud Functions is in limited availability, but what's released today is the FN project, which is an open source serverless framework. And these are all examples of open source serverless frameworks which you can use, where you can deploy the serverless infrastructure on your own hardware of choice. And if you get a provider who also gives you the option of running these in production, then you can seamlessly transition back and forth between your owned infrastructure or a cloud provider's infrastructure. So the FN project is our serverless framework. It's open source. It's part of the Cloud Native Compute Foundation. OpenWhisk is IBM's serverless framework. OpenSAS and Kubeless are both open source projects. And these are all great ways to run serverless and have a little bit more control over what you're doing. Also, it lets you do what I would call an own serverless model, where you can start out by testing, developing on a cloud serverless platform for efficiency. But then once you reach scale, where you actually have a large application global scale, then you can redeploy it on your own set of containers, like we talked about earlier, and actually build out your own global serverless cluster to meet your exact needs. So, top 5 reasons that you need serverless. Number 1, your sysadmin quit. Number 2, you got a million free queries or 2 million free queries or whatever they're giving out now in cloud trials, and you have to use them up. Coincidentally, this is a great revenue center for companies like us. So please get our free trial, exceed the quota, and then become a paying customer. You're already doing microservices and want even more complexity. We all want more complexity in our lives, and this is also a great way to keep your job too. You have a short memory, and you like applications with minimal state. And finally, someone else is paying the bills, you just want to code. So this has been my MO for a while. I like playing with cool emerging technologies because why not? All right, so last technology we're going to cover is machine learning and AI. So this is all the rage now. We all know that machine learning and AI is a huge market for building out new algorithms. The frameworks have become quite developed, but they all have the same basic principle behind them, where you have a bunch of hidden layers in a neural network. You provide inputs into it, and then it goes through a bunch of hidden layers. You get an output, and then you do some sort of reinforcement training where you, based on the output, you try to correct and say whether this was a right or wrong output, and then the neural network changes over time to accommodate and actually solve different problems, which would be difficult to code up programmatically. The DeepMind team recently used this technology to beat professional StarCraft players. So besides just beating people in Go and chess, they also figured out how to build a machine which can play StarCraft better than pro players. This is a view of kind of the neural network of the machine. So on the bottom left, you can see what the machine sees in raw observations, then the parts of the neural network which get activated based upon that vision, what it's considering to do, and then probably the most interesting part is the right side, its outcome prediction. So the interesting thing about watching algorithms like this play against humans is they're quite good at some things which humans are quite bad at. So humans are typically very bad at making unbiased judgment calls about whether they're winning or whether they're losing. When should you engage? When should you not engage in a war simulation like this? The computers do this perfectly. So they know that I have more units than the enemy. I'm going to attack now. I have less units. I'm going to defend. And even if they lose on small micro-management, they tend to win on outcome prediction and larger scale decisions. There's a bunch of different machine learning frameworks which you can take advantage of to do this yourself. So TensorFlow by Google, Caffe, Microsoft CNTK, MXNet Torch, DL4J, which is a Java-based framework, Chainer, Keras, Theano. And all of these technologies fed into the massive amount of computers eventually are going to reach a point which we euphemistically call the singularity, where machines exceed the processing capability of humans. So it's coming soon, and I have a simple model for predicting when this is going to happen. So the first condition for this is we need to have enough data to represent the physical world, right? So the machines need to be able to actually simulate all of us. So simulating us, there's 7.2 billion humans, 6.2 billion nucleotides. So you need 1 × 10 to the 19th bytes. That problem is solved. There's more storage space than there is human DNA. In the Earth, there's 1.325 × 10 to the 37th data. So we're still not quite there, but we're rapidly approaching that. The second thing is you need technology which can actually rapidly expand the processing capabilities of the computers. Google's been building tensor processing units to accelerate machine learning algorithms. Also, IBM has been building quantum computing. So they have qubits computers which can do processing. The interesting thing about quantum computing is they're good at solving problems which are very hard for traditional computers. A lot of scientific biological simulations are exponentially hard. NP-complete problems are also very difficult for computers, whereas quantum computers are ideally suited for these sort of problems. And the last thing you need full automation of all this technology. And we're getting there as well. So I like 3D printing. It's a great way to kill time. You can turn things in the virtual world into physical items. And they've actually built a 3D computer or a 3D printer which can 3D print itself, almost. I think it's like 95% of the components are 3D printed. And it can also 3D print its own parts, so you can assemble a machine from the parts built by the machine. So this is what the robots will be using, just larger versions of this when they come down and take over. And this actually has all been predicted. So nothing I'm saying here is new. We knew all this decades ago.
In the 21st century, a weapon will be invented like no other. This weapon will be powerful, versatile, and indestructible. It can't be reasoned with. It can't be bargained with. It will feel no pity, no remorse, no pain, no fear. It will have only one purpose: to return to the present and prevent the future. This weapon will be called the Terminator.
Okay, so that's the future, unfortunately. So I hope you guys enjoyed the presentation. You can find out more about what we're doing at Oracle with developer technologies at developer.oracle.com. And I'll leave you with the final mandatory Oracle slide, which is don't trust anything I said. And thank you guys very much for coming to the presentation.